All right, guys, welcome back to lesson number 9. This video, we're going to talk about how we can prove or disprove differentiability at some value. And so, you guys, we talked about in the second video that there's 3 places where something's non-differentiable. One is when we have a cusp or sharp corner. A second one is where the function is strictly not continuous. And the third one is where there's a vertical tangent line. So if we want to prove or disprove if a function is differentiable, then we have to actually make sure that those 3 conditions do not apply. So the first thing we do here is we look at to be continuous. We want to make sure that it's continuous. And I like this part because this is where we go back and review the definition of continuity, and we use the 3 steps that we want to actually apply. So I'm going to go through this one pretty quickly because we've actually done this already before. But in order for something to be continuous, remember that the function has to be defined, the limit has to exist, and that they have to be equal to each other. So if I want to find out where the function is defined, so where f of -1 is in our particular example here, remember that we always look at the equal sign, right? It's always where the equal sign is. So it's up here, then we use this function. If it's down here, we use this function. So since it's greater than or equal to, I don't really care that it's greater than, all I care about is that it's equal to. So since it's up here in the top, I'm going to go ahead and plug -1 into my top function, right? And then I'm going to evaluate that. So I got 1 minus 1 minus 3. So I get the value of -3. So I know the point -1, -3 is defined on this function. The second part that I want to do, I'm going to change the color up here a little bit for us. So the second thing I want to do is I want to find out my limit. Does my limit exist? So we've talked about this many times before that if I have a greater than, less than, I have to do a left and right hand limit. So I'm going to go ahead and do the right hand limit, right? Greater than is right hand, just because we just found that value, right? So that's not really hard to do. So x approaches -1 from the right of our function. And again, we plugged it into x squared plus x minus 3. And we get that this is -3. And then our left-hand limit, the limit is x approaches -1 from the left. And I'm going to go ahead and just write down, we could write f of x here, but just for the purposes, I'm going to show you guys that I'm plugging into our bottom function, because again, less than is L for less than and left, right? L. So I'm going to go ahead and put -1 in here. So negative of a -1 is +1. 1 minus 4 is -3. And then we have to also remember, ladies and gentlemen, that since the left-hand limit is equal to the right-hand limit, we have to say that the limit as x approaches -1 of our overall function has to also exist. Okay, so -3. And then the last thing that we can say about continuity is the fact that, okay, we found our point. It's defined at -3. We found our limit. It's actually at -3 as well. So since they're both equal to -3, we can say that the function f of x is continuous at x equals -1. Okay, so that takes one of our check marks off. So we have one of the ones to do. And yes, you do have to show this for differentiability. And like I said, it's a good little review from what we did before. All right, so now let's talk about differentiability. All right, so to be differentiable. So go ahead and write this long word out. And the second example, the last example I'm going to do for you guys, I'm going to actually just write diffy right here. All right, so to be differentiable, first thing we got to do is we got to find the derivative of this. We actually have to find this function, this derivative. And so we're going to go ahead and write this piecewise function out again, but now we're going to find the derivative of the top, which is going to be 2x plus 1 using the power rule, or so the product rule. Sorry, the power rule. I was right the first time. The power rule, and the second one is going to be -1. Okay. We have to look and see if there's a vertical tangent. So that's one. We know they're not, right? We know that these are just lines. These are also curves, so there's no vertical tangent here at all. So we can move on from that. And the last thing we have to do is now compare our derivatives and make sure there's no sharp corners. We want to make sure everything is pretty good with that. So first thing we're going to do is we're going to find the limit again as x approaches -1 of the right. Let's go ahead and do the right first. And so greater than is 2x plus 1. I plug in a -1 here. I get -1 times 2 is -2. -2 plus 1 is -1. I find the limit. Remember, what we're doing right now is we're finding the derivatives. We're finding what our slope is going to be at -1 of our function. So that's what we're doing with these problems. And so we get that this is also -1. So guys, this tells me that if I were able to graph this function, this piecewise function, at x equals -1, I would actually have a tangent line And I could find that slope. The slope of the tangent line would be -1 because the left-hand side and the right-hand side both have a slope of -1. So if I were to draw the point of tangency at -1, then I would actually have that. So that's actually really important. And that's all that we need in this problem to actually solve the problem. I can now say that since the limit as x approaches -1 from the right of, be careful here, f prime of x is equal to the limit as x approaches -1 from the left of f prime of x, then I can say that f of x is also differentiable at x equals -1. Okay? Now, I just want to say one more thing, and I should have said this earlier. It's what happens if it wasn't continuous? What happens if we got to this step and the limits weren't correct or these weren't equal to each other? Then this part is just void. You don't even have to do it. You don't have to do it. If it's not continuous, it cannot be differentiable. Okay, so that's just a moot point for that. All right, so let's go to our last example. And so let's talk about one. And you guys know I show you one where one is differentiable, and then we're going to show you one where one's not, right? So that's what we're going to do here. We're going to go ahead and start back with what we did here, and we can say prove that it's differentiable at x equals 4. So we're going to do the same thing again. It's always good to practice, right? So to be continuous. So let's look at to be continuous first. So we're going to go ahead, and again, ladies and gentlemen, I got the equal sign in the top function. So I'm going to go ahead and plug in f of 4. And I'm going to go ahead and plug in to our top function. So I get that this is the square root of 9, which is going to be 3. So f of 4 is equal to 3. If we go ahead and look at number 2, we're going to find our limit. And again, because it's a piecewise function, we're going to have a left and right-hand limit. I found the right-hand limit already. And I'm going to go ahead and write the function out this time. Again, you can put this f of x if you want to, but we've already found it. So why not? Let's go ahead and write it out. The limit as x approaches 4 from the left. It's going to be this crazy function right here. Right? So that's going to be 4. And then minus the cube root of x minus 3. So this is going to be 4 minus 3 is 1. The cube root of 1 is 1. 4 minus 1 is 3. So we have now said that the limit as x approaches 4 of our overall function is equal to 3. And then lastly, ladies and gentlemen, we can say, again, definition of continuity here, that f of 4 is equal to the limit as x approaches 4 of f of x. So I can say that f of x is continuous at x equals 4. Okay, at x equals 4. So that's a good part for that right there. Okay, good part for that. And so we're going to move on to this. So our continuity is out of it. We can look at vertical tangents here in a second. So to be differentiable, again, we're going to do, I said I was going to abbreviate that, didn't I? So in order to do this, I'm going to take our derivatives of this. So remember, this is just going to be x plus 5 to the 1/2 power. So this is going to be 1/2 x plus 5 to the negative 1/2 times 1, right? This is going to be our chain rule. And then I should put a derivative point right there. And then the derivative of 4 is just 0. And so again, we have this raised to the 1/3 power. So we're going to have negative 1/3. I'm going to rewrite this again for us so we can have it here. To the negative 2/3 raised and then times 1. So really quickly, let's go ahead and rewrite that. Okay, so I went ahead and rewrote these things for us to do here. We have to check for vertical tangents, which means that our function is not defined here. If I plug in 4 here, I will still get a defined value. If I plug in 4 here, I get a defined value. So at x equals -5 and x equals 3, then I would actually have vertical tangents over here. So we are good on that aspect. And so the last thing that we have to do then, ladies and gentlemen, is look at the limit as x approaches 4 from the right. And so 4 from the right would be this function right here. We're going to find out what this value is. So we're going to plug in 4. We're going to get 1 over 2. Let's go ahead and just do that. And then we're going to get 4 plus 5 is 9. So we're going to get that this limit is going to be 1/6. And then we're going to find the limit as x approaches 4 from the left. And we're going to do negative 1 over 3 times, again, 4 minus 3, right? 4 minus 3, which would be 1 to the 2/3 power. And it's just going to give us negative 1/3. So clearly these are not equal to each other. So since they're not equal to each other, I can say that since the limit as x approaches 4 from the right of f prime of x, again, be careful with prime, does not equal the limit as x approaches 4 from the left of f prime of x, you can now say that f of x is not continuous, or sorry, not differentiable at x equals 4. Okay, so there you have it. There you have it. It's a long, crazy thing to do. But again, at any moment in time, if anything happened where this was, this failed, then this is not even part of it. Most time, I told my students this, guys, most time if we're asking to prove something's differentiable or not, I would say 99 out of 100 times it's going to be continuous. They want to know what's going on over here in this particular part. But this is all the work you have to show for the notation, and I hope this helps, and we're going to see you guys in the next lesson when we talk about the chain rule.